Linux, one of the most professional, difficult, and also most famous OS in the world. But have you ever wondered how such an amazing system is made? What is behind the scenes of this magnificent OS? This is what we're going to find out in this video, so stay tuned. To understand how Linux is made, we must stop looking at it as a product and start looking at it as a collection of loose components. If you want to build Linux right now, you do not start with an installer. You start with three things: the host system, the computer you are currently using, running Ubuntu, Debian, or Fedora, which will act as the factory; the source code, the human-readable C and assembly files for the kernel and the GNU tools; the compiler, the tool that translates that human text into machine binary. We are not installing software, we are compiling an operating system. This is the step-by-step engineering process. Step 1. The partition and the hierarchy. Before a single line of code is compiled, we need a place to put the new OS. We format a partition on the disk, usually ext4. Inside this blank partition, we must manually create the FHS, the File System Hierarchy Standard. This is the skeleton of Linux. We create specific folders: /bin for user binaries, /etc for configuration files, /lib for shared libraries, /proc and /sys for the kernel to talk to hardware. Without this specific folder structure, the compiled programs will not know where to look for each other. Step 2. The tool chain, the chicken and egg problem. This is the most critical and difficult conceptual step. We cannot use the compiler on our host system to build the new Linux, because the host compiler is tainted by the host's libraries. We need a pure compiler. So we must build a cross-compiler toolchain. Bin utils. First, we compile the assembler and linker. These tools manipulate binary code. GCC, step 1. We compile a static version of the GNU C compiler. Kernel headers. We install the API definitions from the Linux kernel so the system knows what functions are available. glibc, the C library. We compile the standard C library. This is the interface between software and the kernel. GCC, step 2. Now that we have a C library, we recompile GCC so it links against our new library, not the host's. We now have a temporary toolchain. We are effectively building a factory inside a factory. Step 3. Entering the root. At this stage, we isolate ourselves. We use a command called root, change root. This changes the apparent root directory for the current running process to our new partition. From this moment on, the host OS is invisible. We are trapped inside our new empty directory structure. We are now building the system from the inside out. Step 4. Building the userland, the body. A kernel alone is useless. It needs tools to interact with. We must now download, configure, and compile the GNU core packages one by one inside our environment. For every single package like bash, core utils, make, or grep, the process is the same. /configure, a script scans the system to check what hardware and libraries are available. Make, the compiler converts thousands of lines of C code into binary. Make install, the binaries are moved to their places in ./bin or ./usr/bin. We must manually compile the bash shell so we can type commands, the core utils so we can list files and move them, and the text editor like Vim or Nano to edit config files. Step 5. Constructing the Linux kernel, the heart. Now we build the actual kernel. This is the most complex single piece of software in the build. Download. We grab the latest source tarball from kernel.org. Cleaning. We run make mproper to ensure the source is perfectly clean. Configuration. Make menu config. This is the most crucial step.
A graphical menu appears. We must manually answer thousands of yes-no questions. Do we want support for NTFS file systems? Do we need drivers for NVIDIA or AMD GPUs? Do we enable networking protocols like TCP/IP? Do we compile these into the kernel static or as separate files, modules? If we choose wrong, the hardware won't work. Compilation. We run make. The compiler processes millions of lines of code. It creates a compressed file called VM-linuz, the bootable kernel image, and a system.map, a symbol table for debugging.
Step 6. The bootloader, the ignition. The computer motherboard, BIOS, or UEFI does not know how to load our new kernel. We need a bootloader. We typically compile and install grub. We install the grub binaries to the hard drive's master boot record or EFI partition. We create a config file, grub.cfg. This file tells the computer the kernel is located on partition 2 inside the boot folder. Load it into memory and start executing. Step 7. The init system, the nervous system. When the kernel starts, it is dumb. It only knows how to manage hardware. It doesn't know how to run a web server or a login prompt. It looks for exactly one program to run, PID1, process ID 1. We must compile and install an init system. This is usually systemd or sysvi. We create scripts that tell the init system what to do. Mount the hard drives, start the network, show the login prompt. Conclusion. The first boot. The process is complete. We reboot the machine. The BIOS loads grub. Grub loads the VMLUNZ kernel into RAM. The kernel detects the CPU and memory. The kernel mounts the file system we created. The kernel executes the init system. The init system spawns the bash shell. We see the command prompt. We have not just installed Linux. We have taken raw text files written in the C programming language, passed them through a compiler we built ourselves, and assembled a functioning operating system. That is how Linux is made. If you found this video informative, and if you learned something from this video, so please like the video and subscribe into the channel so you can see more like this video.